before? Anybody here who has seen me before? Yes? When was that?
Zoom meeting.
Zoom, okay. I was once here in Harrisonburg many years ago with Chris Lawrence. I don't know if you guys remember Chris Lawrence. He was an extension educator in this area, and we did a soil compaction field day with some people from Soil Dynamics Lab, and I think Mike Hubbs from NRCS was here from that meeting, and it was very nice to be here in Virginia, in the Shenandoah Valley. Again, I learned that about the Shenandoah Valley when I was here, and it's great because I work at Penn State University. I'm actually originally from the Netherlands, so that's why I have an accent. I'm never going to get rid of it. I've given up on it. So it's not, I'm not Pennsylvania. Well, I always like to say, you know, Dutch is not Pennsylvania Dutch, it's Netherlands Dutch that we speak back home. But then I say, well, I'm Dutch, but now I'm also Pennsylvanian, so I'm real Pennsylvania Dutch. You know? Well, the Shenandoah Valley is much like Pennsylvania. A lot of Pennsylvania is very similar, so we have a lot of similarities in our soils, with the limestone soils especially being very common. So I think a lot of things that we learn in our state are also applicable to what you guys work with, although perhaps not everybody is from the valley here, but I think most of you. Well, my responsibility at Penn State is I'm soil management specialist, so I always talk about how to maintain soil health, how to improve soil health. So as an illustration of the importance of soil, I think I'd like to impress on you how important it is to take good care of your soil. I consider it, farmers have a privilege to take care of the soil. It's a challenge, but also it's a responsibility, because soil is just limited. So if we consider the earth to be like an apple, this represents the globe, that you know that the land surface of the earth is only 1/4 of the earth, of the globe. It's impressive when we think about it, because we don't spend a lot of time typically on the water, but 3/4 of the earth is water, it's ocean. So we only have a land surface which is 1/4. However, 1/2 of that quarter, that land is under ice caps or high mountains. So we only have 1/2 of that left, which is the dry land basically, and land that is not under ice caps. But of that land, 3/4 of it is either too dry, too hot, too wet, even too cold. So we're only left with 1/32nd part of the earth being actually suited for crop production. It's not all in crop production, but it's suited for crop production. Still a large part of that is under natural vegetation too. But you know, when we think about the soil, it is really only like this, I like the term, the skin of the earth. So we take that skin of that apple, and that represents our soil. Do you get a little bit the message that our soil is a limited resource, and it is also very fragile? You know, when you think about your own skin, I think it becomes clear how important our skin is for our well-being, and the soil is just as important for the well-being of our living here on the earth. So that is a bit about soil, the importance of soil. But we have a problem, and there's a lot of soil that is being degraded. Soil degradation is a very important problem, basically, what we are facing. But this was done many years ago, these data that was collected from specialists all over the earth. some scientists from the Netherlands, they collected this information and they interviewed a lot of specialists from all over the world, asked them to estimate the area of land in their jurisdiction, basically, that suffered from different types of soil degradation. When they distinguished water and wind erosion, nutrient decline. You know, nutrient decline is where the soil's been exhausted. We don't use that term a lot anymore. It used to be a very big reason for soil degradation in the United States too. Soil exhaustion here in the East, it was a very common. It was basically a combination, in those days it was a combination here of soil erosion but also depletion of the nutrients in the soil. And since there was no fertilizer at the time, it was before the era of fertilizer, and the nutrients were not replenished, the soil became poorer and poorer. Well, this is still happening in other parts of the world too. Soil pollution and salinization are other problems. Acidification, where the soil just becomes more and more acid. When you don't lime your soil, in some parts of the world they don't use any lime, and the soils become very acid. It's a form of degradation. Soil compaction. I mean, I was here talking about soil compaction. Do you think soil compaction is becoming less of a problem or more? What would you say? More? Going up, no? The equipment that we are using in farming now becomes bigger and bigger most of the time. Sometimes small-scale equipment can cause a lot of compaction too. Perhaps some of you guys use steel wheels. Well, they are not the greatest for soil compaction. Even animals, they can do a lot of trampling. So we need to watch out with that, take care of it. Waterlogging is another form of soil degradation. And finally, the subsidence of organic soils. I don't know if you guys are familiar with organic soils. In Virginia, I think you do have an area where there are form of peat. There are peat soils. Do any of you farm peat soil? In the east of Virginia, I think there is an area, no? Am I wrong on that? I thought there was an area, very black soils, peat soil. Yes, correct? That's only very far from here. So you guys perhaps don't farm that, but you know those used to be marshes that were underwater. That peat was accumulating for a reason, was because there was no oxygen for microbes to decompose that organic matter. And so that soil became completely organic matter. But we find out that when we drain it, it becomes very productive. There's a lot of nutrients in that organic matter and has good properties for crop production. But now the microbes are starting to work on that, and that soil just subsides. And you know, there's places in the world, like in Florida, I've seen a picture where a person, they had built their house at the ground level. They build them on poles, because the poles have to rest on the underground, which is sand, drilling the posts through the peat into the sand. And after many years, they could park their car underneath the house because the soil had completely decomposed and went up in the air as CO2. Anyway, that's just, I always like to tell that because I just think it's interesting. There's so many different types of soil, you know, and they all need to be cared for differently. By the way, that in the Netherlands, we also have a lot of peat soil, and the way to avoid that subsidence from becoming so bad is to keep the soil saturated with water. Of course, now you can't get in the field so they keep the water table very close to the soil. They regulate it. In the Netherlands, there's very good water control, and the lands are surrounded by canals. And then they drain it during the times of the year when they have to get in the field. They lower the water table. It's all because that subsidence, you try to control it, but you can't really, and it just happens still, and just slowly but surely you will lose that, and in the end you will have the subsoil, which is typically sand. Now in our neck of the woods, we are mostly concerned about soil erosion as our primary cause of soil degradation. In Pennsylvania, we are like 60% of our cropland is highly erodible land. So on sloping ground, I think here in the Shenandoah Valley and this area, it's no different. So soil erosion, even worldwide, when we look worldwide, it is the biggest cause of soil degradation. And we really have to find ways to reduce soil erosion. Now there is soil erosion by water and there's soil erosion by wind that we consider. Those are the traditional types of soil erosion, but there is also soil erosion by tillage. That's different, but it works in combination with, for example, water erosion. How does that work? Well, whenever you plow the ground, you move some soil downhill. So over here we have some pictures of different types of tillage. When you're on flat ground, you don't have that movement, but when you're in an undulating landscape, it's just physics. Some soil will always move downhill with plowing. If you plow downhill, you move most. If you plow deep, you move more. If you plow uphill, you move less, but still some soil will fall down the slope. If you use a moldboard plow, typically you move more soil. If you use a chisel plow, you have less tillage erosion. However, if you go slow, you move less. If you go fast, you move more. So today, with our large farm equipment and the tillage we do, we often like to move very fast, and then we still can move significant amounts of soil. But this tillage erosion, it does not rely on water or wind, it's just because of the tillage. However, when we loosen that soil, it goes downhill, and then it ends up where we have more runoff. And so you kind of set yourself up for increased water erosion. Kind of works in tandem. You guys probably are just as familiar as I am with clay knobs. Clay knobs are, you also have rock outcroppings, no? Here. Often the soils in this area, one of the differences I often see in Shenandoah Valley compared to many of our soils, we have some pockets that are similar, but it seems that rocks are more often close to the soil surface. The limestone comes, you see a lot of limestone outcroppings. Well, those things can grow as we do a lot of tillage. So what are some of the effects of soil erosion? For us, working in agriculture, the productivity of the soil is really affected. Because soil erosion, it reduces soil depth, it removes surface soil, we lose the topsoil. That's where we then see clay knobs and things like that happening, where the topsoil is now completely gone, or where we have plowed in now the topsoil with the subsoil. Because you know, in our soils, they're very unique in a way, where we have a silt loam surface horizon and then a more heavier subsoil. Clay loam, typically, clay, heavier texture. So when we lose that surface horizon, which is a lighter texture, we end up with a heavier soil, which is more difficult to manage. It becomes more difficult to get a good stand. The soil is typically in difficult state, like it's either too wet or too dry. And then when it's dry, it gets very hard. When it has a lot of clay, so we really should try to conserve that silt loam surface horizon. Of course, that's also where we have our organic matter. So the organic matter is really the most fertile part of our soil, and that is all concentrated in that top layer, and that we need to protect it by all means from erosion. But then, of course, we also have off-site effects on surface water quality, and it is a big concern also still, even today. I'm always surprised when I drive down in Pennsylvania, like I pass the Susquehanna River, and I'm noticing many times it is looking awfully brown. It's not clear water. Where does all this come from? Probably a lot of it comes from our farmland, unfortunately, still today. In the United States, we have really should have learned our lesson, I think. We're still learning and trying to deal with this, but I actually came here because of this, what we have had in the past. So we had a big shock therapy, basically, in the 30s with our Dust Bowl. It was a national disaster for us. What was happening, and I think it is a lesson from history that we should take to heart, how we can become very greedy and our greed starts to take over judgment, sound judgment, and taking care of the soil is kind of gets lost in the shuffle. What was happening in those days, in the 1800s, people were still kind of pioneers moving west, taking land into production, new land, and they went into the prairies and started plowing them up. And that soil had a lot of organic matter due to the prairie vegetation, the grasses that grew there. And they plowed them up, and in the plowing, they started to decompose organic matter, and that released a lot of nutrients. So you could get bumper crops just without applying any fertilizer. And in those days, there was a time when they had good rainfall, so it was looking great. And they took out all the vegetation and plowed from fence row to fence row. But you know, they forgot that that soil was very fragile, and also the climate was very fragile and very variable. So you had a wet period, but now you had a dry period. So in the 30s, a drought started. But now the prairie vegetation was all gone. That was protecting that soil from erosion. And they had planted mostly, they were planting wheat too. That was like a monocrop cultivation of the same crop every year. So that annual vegetation, now that it didn't grow anymore, the soil was completely bare. And now it started blowing. And that happened predominantly here in this area of the country, northern Oklahoma, western Oklahoma there, northern Texas, New Mexico, Colorado, Kansas there. That area was very heavy. This is a bit of a timeline of the Dust Bowl. So in 1931, that's kind of started, and it became really bad. 1932, 1933, 1934, they estimated that 35 million acres had been completely destroyed for crop production. That land is now in kind of a grassy vegetation typically. It's still not usable anymore for crop production. 100 million acres lost all the topsoil. 100 million acres. Do you know what about the cropland acreage is today in the United States? Just put in perspective. Anybody know how many millions of acres of cropland we have in the United States? I usually use the number 300 million. That's around what we have. If you lose 100 million acres of topsoil, that's a lot. That is what we were talking about in those days. And 125 million acres were losing part of the topsoil. So it got so bad, I came here because I got very intrigued with soil erosion as still being such a big problem in the world. And also then soil conservation methods have been really developed. Models like the universal soil loss equation was developed here in the United States. And a lot of that work was because of the Dust Bowl, because we became very aware of the need to do something about soil erosion, and a lot of the technology and knowledge that we have about soil erosion is because of this dramatic event. So in 1935, there was around those times that he had been around for a while, but Hugh Hammond was the father of, we consider him to be the father of soil conservation. Well, Why was he the father of soil conservation? He was very aware of the danger of soil erosion, and he tried to motivate farmers. He was a unique personality. He also went on the radio and he wrote a lot, but he was a motivator also. He knew about how to talk to people. He also tried to motivate the government to do more about soil erosion. But he had a hard time. A lot of congressmen and so on, just like today, we're no different. We often have a hard time getting a message that something is important, because they have a lot of other things to deal with too. So a lot of Congress people were kind of skeptical. Of course, also, they were not all from this area where they had all this dust blowing around. And he had a hard time convincing them. But he was planning to have a meeting with Congress, talking about them mobilizing resources, and he had heard that the dust was coming east. So he was taking advantage of the disaster. And as he was talking to some Congress people, the sky started to become dark in Washington, D.C. And the people were saying, well, what's going on here? Is it starting to rain or what? Well, no, I think it is. It looks like dust. And then he started talking. You guys know that this is the dust from Oklahoma that is here in the sky of Washington, D.C., and it went all the way into the Atlantic Ocean, like 300 miles, and that was where topsoil ended up. Well, then they kind of got the message. This picture, by the way, is from 1935 Lincoln Memorial, and you see the dark sky. It was because of the dust. So that was then when a lot of work really started to happen on soil conservation in the United States. The Soil Conservation Service, which was in the Department of Interior before that, was now moved to the USDA, and that is today the Natural Resources Conservation Service. Also, President Roosevelt, in those days, he was also came really on board. And you know the famous saying, the nation that destroys its soil destroys itself, came from him. It was actually in a letter he wrote to the governors of the states to establish the soil conservation districts in all the counties of the United States, and that's why we have that today. So a lot of work started and a lot of conservation went into place, and that really helped reduce soil erosion. Also what helped then was that the rains returned also to the plains, and that erosion problem kind of dissipated. But it had dramatic effects. Here are some pictures from those days, and you can see how the land was becoming a wasteland after that soil erosion. Tremendous human suffering. We sometimes forget about it. 2.5 million people were displaced from their homes. They ended up becoming, a lot of them became environmental refugees. It was the largest people displacement in the United States that we have known. The people were called Okies. A lot of them went to California, ended up in refugee camps there, like these here, these camps. And this is a very famous picture of Dorothea Lange, a migrant mother in California. So I hope we will never forget, and I hope telling this all to you, so I give you a little context, and you guys are all land managers, farming the soil, taking care of the soil, and I think it is something we never should forget. It is an important responsibility. It is a privilege because the soil is a wonderful resource that we have, a wonderful thing, but it is fragile and we have to take good care of it. Today even, this is not very recent, but you see a bit of the trajectory of soil erosion in the United States. This is from calculations using the universal soil loss equation, or the revised universal soil loss equation. But you see, we're making progress, but we still are losing a lot of soil. Here, about 20 years ago, we still lost 1 billion tons of soil a year, which I think is still too much. So still a lot of work to be done. This is some other data. You know, the Corn Belt is considered I traveled to South America, to Argentina, and talking to those farmers, they were saying they kept monitoring 3 areas in the world that they consider to be the grain belts of the world. Do you guys know which ones those are, the 3 grain belts of the world? Grain baskets? Yeah. Ukraine, Russia, that area, Argentina,
Mississippi.
And then we have our corn belt, basically, the Midwest and Great Plains. What do all those soils have in common, by the way? They're all originally were under the prairie vegetation. And that's why they gained all this organic matter. They are known for having tremendous organic matter, deep organic matter, and being very productive soils. Well, this was a study that was done in the corn belt, so one of those 3 big grain belts of the world, and they used remote sensing to measure the soil loss. So you know when the soil loses its topsoil, it changes color. So they used that, and since a lot of tillage is still happening in the Midwest today, the soil sits often bare. And so you see that very clearly. And with this remote sensing, they were able to monitor all the spots in the fields where there was no more topsoil. To my surprise, I didn't know it was this serious, because I always thought in the Midwest they have unlimited topsoil. But that's not really the case. That topsoil over there is also limited. And they estimated that 35% of the cropland in the Midwest and the entire Corn Belt, which is a huge area, tremendous area, 1/3 of that has lost completely the A horizon, which is the topsoil, where the organic matter is. 1/3. Came a little bit as a shock to me that this is so much. They estimated that 70% is due to tillage erosion. So, you know, tillage erosion doesn't move soil from the field. It doesn't move from the field, but it is moved from the high spots to the low spots. So you end up with deep topsoil in the bottom of the field. But then the water erosion can take that away easily. So 30% of this topsoil loss is estimated to be due to water erosion. And the crop yield reductions, so some studies have been done where they measured crop yields on the areas where there's no topsoil left, and then they compared it with the areas in the bottom of the field. And so the estimation from that research is that on average there's a 6% yield loss every year. Of course, we don't notice it because that's just the way it is, you know. That's just what we have to work with. We don't have a comparison, but 6% of yield loss is pretty significant, I would say. And the estimated economic losses that we have due to this, very significant. Billions of dollars every year are basically lost, because now it's very difficult to now regenerate those soils. It takes a lot of effort to regenerate a soil that doesn't have any topsoil. So still a very important problem, and something we have to take very serious. So, you know, I've worked a lot on trying to help farmers with adoption of no-till systems over the years. And no-till systems are a great way to avoid, say, soil erosion and to improve our soil. And they have 3 pillars. In some parts of the world, they call this conservation agriculture. We use the term no-till system. Systems is what I'm using. It's not only not tilling, but it is a system because you have to have all the 3 legs of this stool. First of all, there is the reduction of soil disturbance, minimum soil disturbance. Then next is the permanent organic cover, to try to keep the soil covered at all times by organic cover. This is so important for many different reasons, for soil erosion control, but also for soil life in the ground, because a lot of soil organisms don't flourish when there is no organic cover on the soil surface. And then the third leg is diversified crop rotations, also very important. You know, you remember all these things were lacking when we got the Dust Bowl. We had a monoculture of wheat, all the soil was tilled, and the soil was bare. And then we got into all our problems. So this is why we have these three legs to the systems of no-till. Why is that? Well, when we plow the soil, it's like stirring the coals in the fire. We break up the aggregates. There's organic matter that is stored inside of aggregates that are kind of clumps of soil. Inside there's the organic matter is stored inside. When we break that open, it is exposed to the elements, and microbes are feasting on that, and that stuff is just being decomposed very quickly. It's like invisible clouds of CO2 follow the plow, basically, is what I'm trying to illustrate here. This is actually from France, a picture where they still do world plowing contests, and they try to see who can plow the most acres in a day. And here they plowed 792 acres in 24 hours. Yay! Wow, a powerful tractor too. Here, I think 550 horsepower tractor. Wonderful. But what are we doing to the soil? Is what I'm thinking of. I like farm power too. I like raw power, man. It's great. Like tractor tracks, pulling at the contests. I love them. Anyway, but we have to think about what we do for the soil, you know. This is from a long-term study at Penn State that I have managed for many years. You see the increase in organic matter, especially near the soil surface. These are actually hands of Mike Hubbs. He was visiting us, and here you have the soil from our no-till and then from the moldboard plowed fields. You see the darker color, you see the crumbly structure. That is because we have taken care of the soil with using no-till practices. Soil cover is so important for soil erosion. Here is the relative soil loss. So compared to completely bare soil, 100% soil loss. Whenever we start to increase that cover, we see that soil loss going down very quickly. We typically use the 30% rule as being the limit between conservation tillage and reduced tillage or conventional tillage, because according to this is from rainfall simulation studies, when you increase the residue covers 30%, you already cut down on the erosion with 70%. So that is why we use that 30%, but it is really kind of still very limited and marginal. But you'll be surprised how difficult it is often to maintain 30% residue cover in our crop rotation. Think, for example, of we grow corn silage. What kind of residue cover do we have after corn silage? Hardly nothing. Or soybeans. We grow soybeans. What do you have in the spring? Almost bare ground. Things like that. Even we found with doing a little disturbance in corn stover, very quickly you reduced that cover below 30%, which I think is a very minimal what we should have. You know, when we think about water erosion, most water erosion, by the way, takes place during intensive rainstorms. So when does most erosion take place in our environment here? For example, in Virginia. What do you think if you think about the rainstorms? When are the rainstorms the most intense? Thunderstorms. In the summer, no? That's when they typically occur. Sometimes we have a hurricane, which is also tremendous. Like 1972, I was 6. I was 6, but 1972, still people talk about it. It was a big hurricane, and that water washed tremendous amounts of soil down the rivers. from the land. Because when we have those intense rainstorms, those raindrops are very big. If we have a gentle rain, it doesn't cause a lot of erosion. Those are not the ones we are really so concerned about. But it's those intensive storms, especially when we need to have that protection of the soil. Those drops are like bombs falling on the ground soil surface, destroying the aggregation, and if there is no cover on the ground, the aggregates start to be destroyed, and that releases the fines, and they start to seal up the whole soil surface, and we get then runoff happening. This is from a study from North Carolina in the southern Piedmont. It was a 6-year study where they compared soil erosion and runoff from a field under natural rainfall over 6 years. This is from about 4 to 6% slope, so not so very steep, I would say. And they compared chisel disc tillage versus no-till. On the conventional tillage, the residue cover was only 9%. You remember the 30% threshold that I mentioned? Well, it's kind of minimal, but here only they had 9%. The average soil loss over these 6 years was 33 tons per acre per year. 33 tons. Interestingly though, 89% of that soil was lost in only 3 events. Well, there was like a few days that they had a lot of rain. That was considered one event. During the 3 days, it was about 3 days, they lost 50% of all the soil in those 6 years. Was lost in only 3 days. I mean, it was close to 200 tons per acre they lost in 3 days. So when you average out, it comes 33 tons per acre per year. What I'm trying to say is we need to protect the soil at all times. That is for me. Sometimes people say, oh, well, the soil is covered most of the time of the year. Like 70% of the year, soil is covered. The rest of the year, it's bare, but that's not a big deal. On average, we're okay. Well, if you get this big event during those days that it is bare, you're really exposed. Your risk is high. In no-till, 91% residue cover. Soil erosion was reduced 97%. And the average soil loss was only 1 ton per acre, which is like the geological. In nature also, we lose a little bit of soil when there's runoff. This is very similar to what happens in a forest. And reduction of runoff was also 33%. You know, when we have the soil covered and it doesn't seal over, we also get more infiltration. I just put this in here. We are working on trying to find ways so that we always have residue cover at the ground. And sometimes in the spring we don't have enough. So we, at Penn State, we did a lot of work on planting green. Why do we use planting green? To get more growth out of our cover crops and to have more cover that lasts. Because if we kill our cover crops early, there is only very little residue, and that is decomposed very quickly, so then our soils are again exposed. I really like hairy vetch. This is from a trial that I do. It only works when you have, say, small grains, and you can get that established on time, but hairy vetch has some magic to it for me. It's like earthworm heaven the next year. When that residue gets decomposed, you see so many earthworms underneath. There's a lot of life in the soil, and it supplies a lot of nitrogen to corn. So I typically only have to use about 40 pounds of nitrogen to get a corn crop and very good yields. This is from the plots. I have this in my tillage study. So here we have a moldboard plot, and this is our no-till in planting green. You see the brown from the hairy vetch, and here we have a clay knob. So with planting green, you plant green into the living cover crop, and then you kill it afterwards. Why do we do that? So that we don't have to kill the cover crop prior to planting, and we get more growth out of the cover crop. At that time of the year, we typically double our cover crop biomass in 2 weeks. So it really increases the biomass of the cover crop. Here is a farmer in Pennsylvania. He has converted his entire corn planter and is planting into rye. I really like the legume prior to a grass like corn because we sometimes enter into some challenges with nitrogen management when we use a grass like this, and it's very strawy, it has a high C/N ratio. You really have to watch that nitrogen management because that is like the microbes start working on it and taking nitrogen from the soil and not releasing it to the corn, which is what we need at that time of the year. So that eventually it is like a bank because it becomes part of the organic matter, but when we need it for the corn crop, it's not available. So you have to manage that. With hairy vetch, you don't see that because it is a legume and it contains a lot of nitrogen that is immediately already available. But for soybeans, for example, you don't have the problem because it fixes its own nitrogen. So that works very well with rye. But this crop residue is providing tremendous protection and also feeds soil life. Tillage also has a tremendous effect on soil life. Earthworms, for example, we think about night crawlers. Those really need residue at the soil surface. They come out at night from burrows that they live in permanently. Those burrows are like 3-4 feet deep. I don't know if you ever dug a hole in your soil and looked at those earthworm nightcrawler burrows and tried to follow them. You see they're coated with organic matter, and you will be surprised how deep they go. 3 feet is not very uncommon. And then you have them, they are typically spaced about this far apart. I challenge you to take a look at your soil. Even you could go out today. You will see they build a little mound. You see little humps in the field. And then when you remove that soil underneath, there is a pencil-shaped hole where the nightcrawler lives. Underneath that is that channel that we dug out here. Well, those really need that residue at the soil surface. If they don't have it at the soil surface, they become very rare. They then eat that crop residue after they pull it at night, pull it into their burrow. It starts to rot, they eat it, they mix it with some soil in their gut, and then they come out and they deposit their excrement at the soil surface. That is shown here. It's kind of a gooey looking first, and then when it hardens, it becomes a stable aggregate, and it has higher nutrient content, organic matter content, and they process a lot of soil every year. So we really like those for our farms, but they become very much reduced when we plow. There are other earthworms in the soil that live more in the surface of the soil. So those are less affected by tillage. But those night crawlers are especially affected. You also see the different types of crops also affect earthworms because some of them are better food basically for them, so they thrive better. Microbial matter is also affected, especially fungal growth in the soil by tillage. This is a summary from many different studies where they looked at short-term, long-term, medium-term, long-term no-till, and they measured the ratio of microbial biomass carbon in conventional, of no-till versus conventional. So if you have 1, it would be the same. So you see over time that difference becomes greater and greater. That is why I'm a proponent of continuous no-tillage, because we see that those benefits accumulating over time. And each time we till, we kind of start back from zero. Perhaps you will appreciate this. When you have done no-till for a long time, for example, on the clay knobs, those clay knobs will start to improve. The soil at the surface becomes better, and that organic matter starts to increase. When we, for example, plant small seeded crops like our forages, you will find that you get a better stand on those clay knobs because of that soil improvement, and that it is partly also due to these fungi that help us like improve the aggregation of the soil. There are some special fungi in the soil that live in a microbial symbiotic relationship with the roots. Those are called mycorrhizae. They're very interesting because they grow inside the root. They go inside of the root cells, and they create little kind of tree-like structures there. That's why they're called arbuscular mycorrhizae. That's another word for that. Arbuscular means tree. Well, they call tree because that little tree-shaped structure inside of the plant cell in the root. It is where the exchange takes place between water and nutrients are passed on from the mycorrhizae onto the plant, and the plant supplies carbohydrates to the mycorrhizae. So this basically increases the size of the root system, and then we get better absorption of nutrients and water, and the crops become more healthy. It also has some other effects that I'll talk about shortly. But you see, when we break up those hyphae every year from that mycorrhizae, they have to start from a low level each time, and therefore they become less prominent. This is the colonization on plant roots between chisel till, disc till, moldboard, and then no-till in soybeans, corn, and sorghum in one study. So you see, with no-tillage, we favor those. Decomposer fungi are other fungi that live in the soil, and they decompose especially highly resistant organic matter, like corn stalks and things like that. And they are also favored by no-tillage, as you can see on these graphs. It's compared no-till versus conventional till, and they took soil from different trials in different states, and you see consistently in no-till we have greater fungal matter than in conventional tillage. Okay, I talked about tillage, I've talked about organic cover. The third leg is crop diversity. And crop diversity is also a very important component of no-till systems. This is some yield data from a long-term tillage, or not tillage, crop rotation trial that we had at Penn State. It's now been discontinued. But we had continuous corn, we have corn soybeans, we have corn alfalfa rotation, and we have a corn oat wheat red clover rotation. And they measured the corn yields. That is what I'm presenting here. Over many years, like a few decades. And this is the average corn yield in continuous corn. So when you just rotate corn with soybeans, you get on average here 7% yield increase on corn. If you rotate it with alfalfa, the first year of corn after alfalfa, there is a 15% yield increase. The second year, these perennials have an amazing effect on the soil because the yield differences are lasting for a long time, even after the pasture has, or the forage has been taken out. Because the second year of corn after alfalfa still had a 10% yield improvement compared to continuous corn. Third year it was 8%, and the fourth year there was still a 7% yield improvement in corn compared to continuous corn. In the corn grown after the red clover hay, there was a 16% yield increase. First year of corn. So you see alfalfa or red clover hay, those legumes have a great effect on corn, especially on a crop that needs a lot of nitrogen. By the way, this was fully fertilized with nitrogen fertilizer, so this effect is not due to fertilizer, but perhaps due to the dynamics of release of nitrogen. That might be an explanation, but there's also other things that the hay does to the soil that improve the porosity. We have those old roots that decompose there, and the organic matter that has been produced and left behind by the forages help to explain these yield increases. You know, the whole soil really starts to change when we don't do any tillage, when we use no-till systems or under pasture or hay production. This was from a study in the Netherlands where they compared the soil profile under pasture versus, they call it arable land, which is just moldboard plowed soil in annual crop production, versus the same, but now they used rota digged as cultivation. What they found was in the pasture, the surface of the soil had a stable soil structure, good aggregation, has organic matter. Then there was no plow pan, and underneath there were lots of biopores from soil organisms, especially from deep burrowing earthworms. So that is kind of the situation we try to emulate with long-term no-tillage also. In the cropland, the surface soil structure was very weak, and I think, well, I see it every day when I drive past, say, fields that have been intensively tilled. The soil structure becomes very weak and it starts to slump. At this time of the year, that it becomes very evident now after the soil has gone through a few freeze-thaw cycles and we get rain. That surface just starts to seal up completely and the surface structure is very weak. Underneath they had a plow pan, and under that plow pan there were very few biopores. You know, those deep burrowing earthworms especially are because they are rare in that kind of a situation. In the rotodict, actually this rotodict arable land, they tried to bust up the plow pan with a deep tillage tool, and they found that yes, it helps temporarily, but after that it actually slumped back in. After they started moldboard plowing again, now actually the plow pan became worse because they had broken it up, but it became more susceptible to recompaction. That really, when you have that stable soil structure, it really helps you with being able to be on the ground better, more time of the year. That is because of improved infiltration and internal drainage of the soil, but also to the stability of that soil. This is a graph. This is from the Netherlands, so the climate's a little bit different than here. The major difference being that the soil is hardly never frozen in the Netherlands and they have a lot of wet conditions. So a lot of drizzly rain in the Netherlands, which I don't miss. But they measured the trafficable days when the soil was fit to be on it, just using some measurements of estimating that. Well, in January, the arable land that I just showed you with that weak structure, that cropland that was plowed, they only had about 7 days in the month that they could really be on it without causing a lot of rotting and soil compaction. But on that pasture, it was more than 20 days. So you can see the sequence here. A big difference in trafficability. My eyes were really opened when I was doing a compaction study at Penn State years back. We were trying to do the worst for soil compaction by using a truck with road tires, 30-ton truck. So we had about 10-ton axle load, road tires, and we went into the spring when the soil was at its worst for soil compaction, most wet. We always try to do the most damage that we could because of our interest to see what kind of yield losses and effects on the soil that would have. Well, interestingly, we had continuous no-till. We had a case where we had deep-tilled the soil 2 years prior. Then we had a case where we had deep-tilled the year prior. And we had a case where we had subsoil that spring. And then we were on it in the spring with a big truck here with the road tires. Well, this first picture was long-term no-till. And I'm sorry, sometimes these slides are difficult to see from the back of a room. But you see very little indentation in the ground. That soil support in that equipment still very good. In the 2-year-old no-till, so this had been deep ripped 2 years prior, we saw that the indentations of the tires was about 3 inches deep now. So now we're going to see ruts in the field. This was subsoil the year before. Now we are going to be more like 8 inches deep, creating ruts. Of course, now you can hardly plant into that anymore, and you have to do remedial action. And here we got completely stuck where we have subsoiled that in the spring, and we were on it like a few months later, or a month later. So this really showed to me that the trafficability, that is really a reality. All right, I want to share a little bit about integration of livestock with our no-till system. I got really interested in that because there's some now more interest in looking at the benefits of integration of our livestock on the land again in our crop production. You know, we have really excluded most of the livestock from the farmland, and they're now all in barns. That is the system we have gone through. But we have lost something because, for example, grazing livestock, what do? They stimulate cover crop use and cover crop management. We try to get cover crops now established quickly if we want to use them for grazing. And we also use good management practices. It encourages ecological diversity just to have the animals on the land. It boosts biological activity in the soil, for example, by using manure, the manure from the animals, and then the urine, saliva even. There are some studies being done that show that the saliva, when the animals eat grass, it has a certain effect on the grass itself, and a biostimulant basically. So that is also of interest. Just things we are now starting to think about, and there's often very limited research about that yet. Grazing also is a great way of recycling nutrients. That was really an eye-opener for me when I studied this on one farm. This farmer had transitioned from conventional crop production to complete grazing operation, and he was doing no more tilling. He was using a lot of diversity in his operation, but he was really focused on soil health and on grazing. Almost, he tried to graze the whole year, but he's in the north of Pennsylvania, where our growing season is about 150 days, so very challenging. But he has been able to extend his grazing season, and now he grazes 300 days in the year. 300 days. Amazing, because he uses a lot of stockpiling in the field. He has sold all his harvesting equipment, so he doesn't make any more hay. And he was telling me that he used to have a huge fertilizer bill, like $16,000 a year, and that had been reduced to a very small amount, about $1,000 a year on fertilizer or less. And I was just sitting there thinking, how is this ever possible? Because he had very good forage production. His grazing was very productive, he had very good animal gain, and his forages produce a lot of biomass. And I was thinking, how can these grasses and all these forages be so productive if he doesn't apply any fertilizer? Well, I started to make a calculation of the nutrients that he was removing from his farm. Well, if you think about it, if you have a beef operation, the only nutrients that are leaving the farm are in the animals. So I kind of estimated that, how much that was. Then I compared, the other thing was, since he didn't make any hay, he bought all his hay for the 2 months in the year that he had to feed hay, and I calculated how many nutrients are in that hay. And lo and behold, the nutrients in the hay was about the same as the nutrients that he sold of the farm in his animals. So it all started to click with me, and I compared it with if he had made hay on his whole farm and sold the hay of the farm, what kind of nutrients would he have had to replenish? You know, we talked about this soil exhaustion thing. Well, exhaustion happens if you just keep removing and not replenishing. And I found that on the nitrogen, he would have, well, on average for all the nutrients, it was about 10%. So he removed only 10% of the nutrients that he would have removed if he would have made hay on the whole farm. So grazing is a great way of recycling nutrients because most of the nutrients just pass through the animal and are deposited in the manure and the urine again. Now, there are also some potential threats with grazing from especially soil compaction. and then that can also lead to soil erosion if we end up with a bare situation. So those are some conditions that we are concerned about. And I did some studies working with some farmers to look at this. We had one study in the south of Pennsylvania on the border with Virginia, Maryland. We looked at cover crops after corn silage and grazing them versus cover crops after small grains and grazing those. And the farmers were some of them were new to grazing, and they started to graze those cover crops and integrating livestock. These were all long-term no-tillers, and they had very good soil health already. But they had to learn about the livestock management. They used mobile fencing, and they would move the animals every day. And then back fence, they also had mobile water. We helped them also with installing that in our project. But we wanted to look at the effects on the soil and if this would potentially improve soil health. Well, overall, we didn't find that the grazing did either any damage or any benefit to the soil. And unfortunately, we looked at different soil health indicators, and I had hoped that perhaps we would see an improvement in biological activity or so, but we didn't really see that. All the indicators were already very high, so perhaps it was just because of that we didn't pick that up. I don't know. The only difference that we saw was where the farmers would graze the cover crop after the small grain harvest versus double crop soybeans. So these were the only significant differences that we saw. So we had the graze cover crop, and we saw then a drop in the infiltration rate when comparing that with soybeans. And that was consistent for 2 years. Now the infiltration rate in the soybean was still very good, was still very high, but it was higher where we had the grazed cover crop. And this is something that I now hear a lot of people about, really recognizing soybeans are really a weak factor in our crop rotations as far as thinking about soil health. During that soybean year, you basically lose your soil health, and you have to build it back up with other practices to compensate for that. Because they add very little crop residue, the organic matter is very digestible, so it kind of stimulates even decomposition perhaps of organic matter from before. And the soil structure typically becomes worse during that time when we have the soybeans. I'm not saying you shouldn't grow any soybeans, but for example, continuous soybeans, I don't think you should do that. Or perhaps you have to think about how often do I grow soybeans? And then you have to think about practices that you can use to compensate for the reduction in soil health that you have. So from this study, the other thing was the cover crops became now an economic commodity. Every time we're out there grazing, they graze about half and left half each time so that they get good regrowth on the cover crop. Each time they harvested about 1 ton of dry matter per acre per year, per grazing. So the more times you could graze that cover crop, the better the economics was starting to look. Now I want to conclude with just a few words about this. There is an interest in thinking about soil health. Does soil health improve food health? And I just wanted to talk a little bit about that with you. I was approached by a friend of mine. He is a former mushroom specialist at Penn State. So he knows a lot about mushrooms, and he got really intrigued with this compound called ergothioneine, which is produced predominantly by mushrooms or by fungi. Only by fungi and some bacteria. Nonetheless, well, why are we interested in this compound? It's called ergothioneine. Short of it is ergo. We call it ergo. Why is this of interest? Well, it's considered to be a longevity vitamin. What is that? What does that do? This is a potent antioxidant. You know, when our body, when we get older, whenever we live, our body produces some radicals in our cells that damage our the body itself. But there are compounds called antioxidants that combat those radicals that are produced. over time, we don't notice the effect in the short run, but over time, if we have a lot of that damage happening in our body, it results in things like diseases of old age, like Parkinson. Alzheimer's is considered one of the results, and even cancer. So this ergothioneine can combat that. And the medical community is considering this now to be something that we really need, because there is a specific, even transporter in the human cell that is specific for ergothioneine to transport it over the cell membrane that has been discovered. So this ergothioneine is only produced by fungi, but it ends up in plants and in our plant products, in grain, and even in animals. So how does it come there? Because it's not produced by the human body, by animals, by plants. How does it end up in the plants? Is the kind of the question. Here you see some different contents of ergothioneine. And the thought is that it's because of mycorrhizae that live in association with the plant roots. So you know, I talked about the effect of tillage on mycorrhizae, so we got interested in looking at that, and we analyzed the grain from our long-term tillage trial for ergothioneine. And that was really interesting because we saw a consistent trend, no-till having the highest ergothioneine and moldboard having the lowest, and the chisel disc was kind of in between. That was for maize, soybeans, and oats. So this is just recent work that we have started, and we're working with USDA ARS on this. Also, people are specialists with mycorrhizae, and there seems to be a real link between mycorrhizae and this ergothioneine content. And you know, when we use that soil health improvement with no-till systems, we can expect that ergothioneine content to be higher. So in conclusion, I just want to conclude again with my three things: that to take care of the soil is a privilege, but it is also a challenge. And finally, it is a responsibility that we have. So it's not just something we have to take for granted. I think every soil manager has that responsibility. If we use the principles of no-till systems, we can really improve our soil and protect it from degradation. You know, it's great to be in this part of the country, really. In Pennsylvania, Virginia, other parts, we still have a lot of ruminant livestock in our farm systems, and that opens the way for us to make better use of things like cover crops. They can become an economic commodity. And for me, that is a great way of helping us to adopt these practices. You look at the Midwest, where they only grow corn and soybeans, they have no ruminant animals. Their cover crops for them, it's always most looked up as a cost, you know. Now we have to look for the government to help us out, to pay for the cover crops. Because from ourselves, we don't see the immediate effects of the cover crops on our farm productivity, the economics. But we still have that. And so I see the livestock integration in our cropping systems is really something that we can benefit from. You know, it is interesting, in Virginia, now the adoption of no-till, do you guys know how much adoption of no-till is in Virginia? It's 70, I talked to Chris Lawrence about this just to get him, give me some local info. He said, yeah, there's this 2017 census done, and it has the data in it. So I looked it up, and according to the 2017 census, 74% of our cropland in Virginia is no-till. 74%, very high. And then cover crop use, also very interesting. Anybody know what the cover crop use in Virginia is? According to the census, 24%. Nationally, it's only 5%. That's because in the Midwest, they hardly do any of it. And that is where our big acreages are, no? But and Pennsylvania also, we have very high cover crop adoption and no-till adoption as well. We did analyze a transect survey, and we have about 40% cover crop because we included the commodity cover crops, which are the ones that are used for forage. I don't know if in the census they really captured that, because in the census information, the cover crop adoption in Pennsylvania was also about the same as in Virginia. But when we actually looked at Transact surveys, we found it was 40%, because we include the forages that are harvested as well. Because I think even though they're harvested, they're doing a lot of the benefit for the soil. Well, you guys have been a great audience, but very quiet. You don't say a lot, but perhaps that is just a characteristic. If you have any questions for me, just fire them out.